You have made a decision today. It may have been small, which route to take, whether to answer a message, whether to stay in bed 5 minutes longer, and you made it. One choice, one outcome, one version of events that you now call your life. That feels obvious. That feels like the only way reality could possibly work. But here is what no one tells you in school. Here is what mainstream science rarely announces plainly. The mathematics underneath quantum mechanics, the same mathematics that gave us lasers, semiconductors, and MRI machines, does not actually require you to make only one choice. It does not require the universe to select one outcome. The equations themselves, when taken seriously, when followed without flinching to their logical conclusion, suggest that every possible outcome of every quantum event happens simultaneously. In branching, chaotic parallel, non-communicating versions of the universe. This is not science fiction. This is not mysticism wearing a lab coat. This is the many worlds interpretation of quantum mechanics. Proposed in 1957 by a quiet, brilliant, deeply underappreciated physicist named Hugh Everett III. And the reason it still unsettles professional physicists today is not because it sounds absurd. It is because it might be right. To understand why Everett arrived at this conclusion, you first need to understand the problem he was trying to solve. And that problem has a name. It is called the measurement problem. And it is, quietly, one of the most embarrassing open wounds in all of modern science. Quantum mechanics works extraordinarily well. It is the most precisely tested physical theory in history, accurate to 1 part in a trillion in some experiments. But embedded inside it is something deeply uncomfortable. When a quantum system, say, an electron, is not being observed, the mathematics describes it as existing in a superposition, a simultaneous blend of multiple states at once. It is not spinning up or down. It is spinning in both directions, weighted by probabilities, described by a wave function that evolves smoothly and deterministically through time. Then something strange happens. The moment you measure it, the moment any interaction occurs that counts as observation, the wave function collapses. The electron chooses. So it becomes one thing. The superposition vanishes, and the textbook moves on as if nothing strange just happened. But something profoundly strange just happened. You had a perfectly smooth, deterministic equation, and then, at the moment of measurement, you simply declared that the mathematics stops and reality decides. No mechanism, no explanation. Just, it collapses. Physicists called this the Copenhagen interpretation, and for decades, most of them agreed, politely, not to look at it too closely. Hugh Everett looked at it directly. He was 24 years old. What Everett asked was a simple question with radical consequences. What if the wave function never collapses? What if the mathematics is always right? What if the electron does not choose, and instead, the universe branches? Think carefully about what this means. In the Copenhagen view, when you measure a quantum particle with 2 possible outcomes, one outcome is selected, and the other disappears. In Everett's view, both outcomes occur. The universe splits into 2 branches. In one, you observe the electrons spinning up. In another, equally real, equally physical, but inaccessible to you, a version of you observes it spinning down. You do not travel between branches. You do not feel the split. You simply continue, unaware, in one thread of an endlessly dividing reality. Now scale this up, not to a single electron, to every quantum event that has ever occurred in the 14 billion years since the Big Bang. Every radioactive decay, every photon scattering off a molecule, every quantum fluctuation in the early universe that seeded the formation of galaxies, each one a branching point, each one generating new versions of reality, diverging silently, invisibly, at a rate that makes the number of atoms in the observable universe look modest. The number of parallel branches implied by many worlds is not merely large. It is, in any meaningful sense, infinite. And each branch contains a complete, self-consistent universe, with its own stars, planets, civilizations, and versions of you, none of whom can see the others. None of whom would ever have any reason to suspect the others exist. This is where the theory becomes philosophically vertiginous, because those other universes are not hypothetical. They are not metaphors. So in Everett's framework, they are as physically real as the branch you are currently inhabiting. Your sense that this is the universe, the real one, the chosen one, is simply a consequence of the fact that you are inside one branch and cannot perceive the others. It is the same kind of parochialism that once made people believe the earth was the center of the cosmos. Here is where most people stop and say, but if we can never detect these other branches, if no experiment can ever reveal them, then how is this science and not philosophy? How is it different from believing in angels? It is a serious objection, and it deserves a serious answer. The many worlds interpretation does make different structural predictions from its rivals. It treats the wave function as a real, physical object, not a mathematical convenience, which imposes constraints on what kinds of theories can be built on top of it. It resolves the measurement problem without invoking any additional mechanism or assumption. No collapse, no hidden variables, no special role for observers. Just the Schrödinger equation, taken completely seriously, by the scientific principle of parsimony. Occam's razor, the preference for the fewest unexplained assumptions. Many worlds is arguably the most economical interpretation available. The Copenhagen interpretation requires you to add a separate, unexplained process, wave function collapse. Many worlds requires nothing extra. It simply refuses to stop the mathematics where it becomes inconvenient. Furthermore, the phenomenon of quantum decoherence, experimentally confirmed and now foundational to quantum computing, explains precisely why we never observe superpositions in everyday life. When a quantum system interacts with its environment, the branches become effectively invisible to each other at astronomical speed. Not because they cease to exist, but because the correlations between them dissolve irreversibly into the surrounding universe. We do not feel the other branches for the same reason you cannot hear a conversation happening in a room that has been perfectly soundproofed. The isolation is not evidence of absence. And yet, and this is where the discomfort becomes strangely beautiful, the fact that the other branches are inaccessible does not make them meaningless. It makes this branch more meaningful. You exist in a universe where every quantum event has gone exactly the particular way it needed to go, through 14 billion years of branching history, to produce this specific configuration of matter and energy and consciousness sitting here in this moment, experiencing this thought. In the vast majority of branches, you do not exist. In the vast majority of branches, the Earth does not exist. In most branches, no stable atoms form at all. You are not the product of a single, predetermined fate. You are one thread in an incomprehensibly rich tapestry, distinct from every other thread, real in exactly the same way they are real, and improbable in a way that should give you pause every single day. The structure of many worlds does not diminish your significance. It redefines it. You are not the only version of reality, but you are irreducibly this version. The choices made here, in this branch, by this configuration of matter that calls itself you, have no equivalent anywhere in the tree of universes. This branch is unrepeatable. This moment is unrepeatable. That is not nihilism. That is the opposite of nihilism. Constraint is not the enemy of meaning. Constraint is its precondition. Hugh Everett spent the rest of his life after his dissertation largely ignored by the physics establishment. He left academia, built a successful career in defense research, and died in 1982 at 51, before the scientific community began to take his ideas seriously. His son, the musician Mark Oliver Everett, only discovered the full weight of his father's work years after his death. Reading through boxes of unpublished papers left behind in a house full of silence. There is something quietly poetic about that. A man who proposed that every version of events unfolds simultaneously, and who himself died before seeing his branch of history vindicated. So if you are someone who does not accept easy answers, who wants to understand not just what physics says, but what it means, this channel exists for you, not to make reality simpler, to make it honest. Subscribe, if that is who you are.